Hello friends, and welcome back to Webronaq. Here is a question to start with. In 2026, engineers rolled out HTTP/3 across a huge portion of the web. W3 text data from April 2026 shows nearly 39% of tracked websites now advertise support for it. To make that work, engineers swapped out the entire transport protocol underneath, replacing TCP with something brand new called QUIC running on top of UDP. And here is the surprising part. The HTTP layer at the top, the one your browser uses every day, did not change at all. Same methods, same status codes, same headers. How is it possible to swap one piece of the stack without breaking everything else? The answer is protocol layers, and by the end of this video you will understand exactly why that swap worked. Alright, so what exactly is a protocol layer? Think of it this way. A layer is a software rulebook that has exactly one job. The transport layer's only job is to make sure data gets delivered reliably. The network layer's only job is to figure out the route across the internet. Each layer talks to the one directly above it and the one directly below it, and it does not need to know anything about the rest of the stack. One critical clarification here. Only the physical layer, the very bottom, is actual hardware, cables, radio signals, electrical pulses. Every layer above that is software. And most of that software, specifically the network and transport layers, runs inside your operating system kernel. You did not install it separately. It came with your OS. That is why layers are not programs you open. They are rules your computer already follows. Next, let us look at the two models that name these layers. Now, there are two major models for naming these layers. The first is the OSI model, 7 layers, published by the ISO back in 1984. The second is TCP/IP, 4 layers, defined in RFC 1122. TCP/IP is what the internet actually runs on. OSI is the vocabulary everyone uses to talk about it. When a network engineer says, "That sounds like a layer 3 problem," they mean the routing layer. They are using OSI numbering, even if the actual protocol stack is TCP/IP. The two models overlap neatly. OSI's application, presentation, and session layers, numbers 7, 6, and 5, all collapse into a single application layer in TCP/IP. OSI's transport layer maps directly to TCP/IP's transport layer. OSI's network layer maps to TCP/IP's internet layer. And OSI's data link and physical layers together become TCP/IP's link layer. You only need to memorize one model. Just know that when someone says layer 7, they mean your application. Here is the interesting part. How do layers actually stay independent? The answer is encapsulation. When you send a request, your application produces data, say an HTTP request. That gets handed down to the transport layer, which wraps it in its own header, containing things like which port to use. That bundle then goes to the network layer, which wraps the whole thing in an IP header with source and destination addresses. Then the data link layer wraps it again in an Ethernet frame. By the time it hits the wire, your data is nested inside 4 layers of headers, one from each layer. On the receiving side, the process reverses. Each layer reads only its own header, does its job, strips that header off, and passes the rest upward. The application layer at the top never sees the Ethernet frame. It only gets the payload it asked for. That separation is exactly why you can swap out one layer without touching the others. Let me show you exactly this in action. In 2026, HTTP/3 is already running on a significant slice of the web, with W3 text counting nearly 39% of tracked sites' advertising support as of April 2026. The stack looks like this. At the application layer, HTTP/3 sits unchanged. Your browser still sends a GET request and receives a 200 OK, the exact same semantics as always. At the transport layer, QUIC, defined in RFC 9000, replaces TCP. QUIC runs over UDP and adds its own reliability and encryption. Below that, IP routes the packet, and Ethernet carries the frame on the local network. The swap was clean because layers only talk to their direct neighbors. HTTP/3 handed data to QUIC the same way it once handed data to TCP. Nothing above the transport layer had to change. You can confirm all 4 layers live using tshark 4.6.6, the current release of Wireshark's command line tool, which decodes and displays each layer in a single capture. Alright, let us bring it all together. Protocol layers exist for one core reason: modularity. When engineers wanted faster transport in 2026, they replaced TCP with QUIC at the transport layer, and the application layer did not notice. That is layers working exactly as designed. Here is the mental model to keep. The OS kernel owns the lower layers, specifically the transport and network layers, so TCP, QE, QIP routing are all running inside your operating system, whether you think about them or not. Your application lives at layer 7, in user space. And the glue between all layers is encapsulation, headers added on the way down and stripped on the way up, keeping every layer blind to the others. OSI, gives you the numbered vocabulary. TCP/IP is the real running system. Together they explain every network conversation your device ever has. Thanks for watching Webronaq. If this clicked for you, subscribe, and we will see you in the next one.